are watching Darasa Online.
Welcome to our program, my dear students. It's physics time. So today's discussion will be based on the topic known as vibrations and waves, but particularly in the subtopic interference. This is the second part of interference. If you remember, last time we had the interference on the Young's double experiment, and we saw that we can find the position of the fringes using the formula. This is lambda d of that. This is for bright fringes. And this is equals to n plus a half lambda over d. This is for dark fringes. And we come to the formula that you can find the fringe separation as lambda d over that. So we saw how to use the formulas of finding the position and the fringe separation in solving various examples on Young's double experiment. Now, today's discussion will be based on the air wedge experiment and the Newton's ring experiment, as we saw the importance of the concept of waves in our lives. So it's very important to know how the air wedge is formed and what is the Newton ring experiment. So to start with, number one, air wedge. An air wedge, on top of this kind of experiment, it is an experiment which involves the use of plates, two plates. So I'm using this laptop as two plates. We have the first plate which is on the top, the other one on the bottom. So when you have two plates which are pressed like this, such that they make an angle, theta, here. So depending the size of the angle you have, so these are the glass plates which allows light to pass. So you have the arrangement like that, and in between you can put the materials either of any kind of thickness, maybe a piece of paper or a coil of any thickness, and that's how you can form the air wedge. So the air wedge is formed by two glass plates are placed at a point where the point of contact is here, and they form an angle. So by drawings here on the board, we have, this is the lower plates on the surface. We know it's here. And then we have the top plate here. So the angle here is theta. So the light is coming here. This is the falling light on the plates. And we discussed about this now. The arrangement of this, as we did, we had a source of light here from and then this source we have the plane mirror. That plane mirror is supposed to reflect all the rays to the plates. So these rays are reflected after falling on this plane mirror. And then when they come here, they fall on the glass plate, which is inclined at the angle theta. Then these can be observed. Can be observed through a microscope here. So you can observe, after falling here, we know that some of the rays will be coming here, and then they will be reflected, bending. After bending, some of the rays will be passing through the first glass plates, and they going to the second. But after hitting the first plane here, some of the rays will be reflected back, and some of the rays will be reflected from here. They will meet in air, forming two parallel. So these are the parallel beams which are reflected from the two plates, and they will be observed in the microscope. So from there, that's at the end somewhere, you can have the formation of the fringes of the image, as we saw in the Young's double experiment. So that's our point of contact. So these kind of plates, they must have the length, and in between they must have the thickness of the material in between that we normally use as T, and this is L. And this angle is given as the angle of the wedge. So now we can see the arrangement is different from Young's double experiment, but the same question will be asked to find the position of the fringes. So here, observation shows that the image the image will be formed from here, parallel. So the first image will be extending from here. So the first image will be here, which will be dark. The first image is dark. So the image will be extending to the other side, dark, bright, and followed by that one. So you can see the nature of the images will be determined the nature of the top surface. Since the top surface is a plane, so the image will be plane, like that. We want to see the second part. When the top surface is a surface like a sphere, spherical, the nature will be forming something like a circular or a sphere in nature, which is given the name the ring. The ring or the plane. So in this kind of experiment, when observation is observed through the microscope, you can be able to find the distance. The position of the second means the third from the point of contact. So the same concept can be applied here. But the difference is that, if you remember in the Young's double experiment, the first image was bright here, followed by dark, followed by dark. So you see here, that is the center of interference. The first image is given here, followed by other colored fringes. But here, our first image is dark, because that's the point of contact. No light will be passing here. So the formula will be interchanged. As you derive them, you find that the formula for bright, the path reference, we know the formula will be given, this is the path reference, n lambda. And the formula, this will be a half lambda. So that means the condition for producing the dark and bright, the path reference will be like that. And this is applied for the first image. So coming to the air wedge, the first image is dark. So the formula will be for dark. For dark fringes. For dark fringes. And we know when the light is coming from the top surface and then passing to the bottom of the plates, then it will be reflected back as if the path difference, sort of that path difference within the medium is 2t. That n denotes the order where you can find those images. Maybe here, where you have the first image of bright, second, that's the n is the order of the image. So the total distance traveled, when you have the plates, like maybe these are parallel example, when the light traveled from the top down, this is what we call t, and then after being reflected from here, it is traveled twice the distance, that one. So t is the thickness between the two plates at the end here. Can be t, here can be t1, so t2, 3, depending the position of the fringes. So when we talk of t1, maybe this is the first position, the position where the first dark or first bright fringes are formed, depending the nature of the information that we are given. So here, this n stands for the order. For the dark fringes, since this is the first image, so the formula will be lambda. And that here, that's the path difference. From here, we know that this is angle. This is the length of the material which we talk of t. This is the length of the plate. In between, we normally put a material which is giving us the thickness of the material, t. And if you find from this formula, you find that tan of that angle theta will be equals to t over L. If you know the length of the plate, and you know the thickness of the material which is in between the two plates, so you can be able to find that angle of the air wedge. But our discussion here, we're going to see how do we find the position of the fringes, maybe dark and bright. Let's assume that this is the position where you have the nth bright, that is the Tn there, and this is the position where you have this is our XLN. What is Ln means? This is the distance where the nth dark is formed from the point of contact, and this is the thickness corresponding to that nth dark fringes. Maybe can be the second dark, can be T2. this will be L2. That length is known. So from there, you take now, from this equation, you have T, tan of the angle theta, which will be the same as Tn over Ln. Take that as equation number 1. But because this angle is very small, when you have the plates, the angle between them is very small. Mathematically, that angle is approximated to the angle itself. If you take your calculator, if you have a very small angle and you find tan of that angle will be approaching to the angle itself when this is in radian. Mind you, it's supposed to be in radians. So from this number 2, question number 1 you have now, theta, this equals to Tn over Ln. From there you can make Tn the subject. Tn equals to theta Ln. Take this as equation number 2. So if you substitute equation number 2 in here, we have 2 brackets Tn, which is theta L sub n equals to n lambda. So you can find now Ln equals to n lambda over 2 theta. Question number 3. This is the formula which is used to find the position of the nth dark fringe. Suppose you know this is the position of the nth dark, means the second dark. So the next dark will be Ln plus 1, which equals to n plus 1 lambda over 2, number 4. And if you find the difference between the two, if you remember in the previous discussion, we look about the formulas for finding the position of the fringes, dark and bright, and also we managed to find the fringe separation, the width of the fringes. So you find the difference here. Equation number 4 minus 3, it is giving us Ln plus 1. You minus this Ln. This will give us this n plus 1 lambda over 2 theta minus n lambda over 2 theta. So find the difference. This difference is what we call at the fringe separation. We use y equals to n plus 1 lambda over 2 theta minus n lambda over 2 theta. Open the bracket. This will be n lambda plus lambda minus n lambda. The whole of this will be under 2 theta. This n lambda will cancel out, and then we come up with the formula for the fringe separation as 2 theta. So in other books, they normally use S equals to lambda 2 theta. So this is the formula for finding the fringe separation. As we did in the Young's double experiment, if you know the type of experiment you are dealing with, in Young experiment, the first image is bright, and here the first image is dark. So the formula will be interchanging, and then you derived on how to find, you come up with the formula that the formula for the path difference for the dark fringe in air wedge is n lambda. And then we use these formulas to find the fringe separation. Suppose you use the formula for finding the position of the bright, we come up with the same formula. So this shows that when the question is given, you should know how to find the position of the fringes depending the nature of experiment. If you're using Young's double experiment, the formula is different. The formula will be y equals lambda d over that small d, which depends on the wavelength, and d, these are the parameters. But this, for the air wedge, it depends on the wavelength, and it depends on the angle of the wedge. Now, let's see the question. Example 1. Example 1 is talking about the air wedge. Now, we have the air wedge which is formed using 2 glass plates. The length of the air plates are given, means the length are equal, which means 15 centimeters each. And these 2 plates, the way they are made, they are placing a wire in between the two, the wire of this diameter. So mind you, when you have the wire in between them, so you should know that this diameter, you know what that means. The length from the top surface of the plates, or in between, that length in between, sometimes you use to call it the thickness of the material. Step number 1, you draw. The question is given like that. You're looking for that angle, but the length of the plates here is given, and the thickness of the in between, of a material in between, which is given as the diameter, is given as D. So here our D equals to 0.35 millimeter. Our length is given as 15 centimeter. So you are looking for what? You are looking for the angle, that angle in between the plates, which is given the angle of the wedge. That angle should be in radian. Simply, you are supposed to convert these units so that they may have the same SI unit, which will be 35 times 10 negative 3 meter. This is 15 times 10 negative 2 meter. How do we find the angle? The formula we derived. It's not here. If you remember, we said that the angle, tan of that angle equals to the D. We said tan of the angle equals to that side over L. And we say that angle is very small. So in radians, if you are using a calculator, you can find the angle of this air wedge, when it's very small, is approximately the tan of that. So this theta equals to D over L. From there you can find, because you have the values there, our D is given as 0.35 times 10 negative 3 meters divided by 15 times 10 negative 2 meters. And you can see the values will cancel out. You have the values angle, which is in radian. So you take your calculator, 0.35 divided by 15, giving us 0.023 times 10 power negative 1. So if you take that is 223 times 10 negative 4 radians. That's the angle of the wedge. So if you use your calculator, you get that value correct. So that's how you can find the angle of the wedge from these informations. If you know the length of the plates, and if you know the length, the thickness of the material in between, that's how you can find the angle. Sometimes you may be given a question where you're supposed to find the position or the thickness corresponding to a certain order, maybe second order, bright, second order, dark, and so on. The formula, you should know specific formula to apply. But when looking for the angle, this is the correct formula. Part B, find the fringe width, the fringe separation. And in part B, we are looking for Y or S. What is S? The formula is lambda 2 theta. Very important that you know the formula. No need of driving, because when the question is asking to find the fringe width, you're supposed to record the formula and you plug the value which is given here. So you know the angle now, and the lambda is given. So the wavelength is given. Given that the angle is known now, 23 times 10 negative 4 radians. Wavelength is given as 5.8 times 10 negative 7 meter. You're looking for S. Plug the values. S equals to lambda, which is 5.8 times 10 negative 7 divided by 2 times this angle, which is given as 23 times 10 negative 4. So using your calculator, you can find the values of S. 5.8 divided by 46, which is 0.126 times 10 negative 3. Negative 3, this is negative 7, this is negative 4. When you combine, according to mathematics, this is giving as negative 3. This is in meter, or equals to, because it's very small, you can talk about the 1.26 millimeter. So that's the fringe separation. Very simple. If you know the formulas, and the question will be done. So you're supposed to recall the formula for finding the fringe separations, the angle of the wedge, and if the question is asking maybe the position of the fringes, you should know the nature of the fringes, either it's dark or bright. Okay, that's how you can deal with the question talking about the air wedge. So that's our first discussion of today's lessons. So let's see now the second part of the experiment is Newton's ring. Newton's ring. 2 is Newton's ring. Rings experiment. This is an experiment which was done by Newton, and he was trying to investigate whether we can form interference using the arrangement. What is normally done here, you can see the arrangement of the way Newton did. Newton modified the first experiment. He modified this. This was the experiment where we have 2 glass plates, and we saw that the image from here will be a plane fringes. Now Newton was asking a question: what happens if you change the nature of the top surface of the material? So he used the biconvex lens. The top surface now was removed and replaced by the convex lens. You remember this lens here, and the same arrangement. So the same arrangement, and then we have the source here. The same arrangement was there, and so we have the plane mirror, which reflects the light on the surface of the lens. So the arrangement is the same as we did in the air wedge, that we have the source of light which is coming from here. That source of light is falling on the plane mirror here, which is at 45 degrees. After falling, it will be bent down so that it can fall on the surface of the top surface of the lens. Then we know it undergoes several reflection here before reflected back to the where it can be observed in the traveling microscope. So we're going to see now how do we find the formula, position, and what will be the nature of the image formed here. What will be the formula for finding the position of the bright and the dark fringes? Are the images the same? So let's see how do we find the formula in this part of Newton's ring experiment. So we had, this is the top surface, that is the radius. That is the radius, if you remember. This was our Tn, if you remember. This was our x ln in that experiment that you did. So you can see now the top surface here is a spherical in shape, and the nature of the image will be spherical. And when we talk of spherical, there will be of this form. So starting from here, we have the observation shows the image will be of this form. So to form the ring, so this is the image formed will be the rings of increasing distance from the center. We talk of the radius. So here it is R1, maybe. This is R2. That is R3. But here we have the first here is dark. That's the point of contact. The point of contact, if you remember in the air wedge, it was at the end. That's where the image starts extending from here, the other side. But here the center of the point of contact is at the center, meaning that the first image is given the name, this dark. It's not a ring, it's a dark spot. The starting point here is the dark spot. And the way the other image is, this will be the first dark ring, second dark ring, third dark. This is in between we have bright rings. The way I've drawn, at least you can see how the rings are formed. But we have two types of ring here, dark, bright. They are alternating in forming the Newton's ring experiment. Now, since the first image is dark, the formula will be the same. 2Tn will be n. And now the formula changes now. When you derive that formula, you get something like we come up with a formula which is now talking about, because we talk of the 2n equals to n lambda. This was the dark ring, fringe in the air wedge. And when you plug the formulas there, you can come up with so here now, because we don't have the L length, it's now given as the radius. This is the radius of a ring. So if you derive the formula basing on the radius, if you consider, that means if you consider this diagram here, if you want to derive that formula, we consider this is the part of the curved surface here, and this is the center here. Let's take this is our Tn. That's the position where you have Rn, the radius corresponds to that. And if you draw the line here, this giving us this length here is how much? This is the radius of curvature. It's radius of curvature minus Tn. So in the air wedge, we use that concept for dark ring. But here, if you use this concept here, because with the thickness in between, this is the radius of the ring. So use this part of the triangle which is formed here. So R squared equals to this length here is the radius, n squared, plus R minus Tn squared. Want to see the formula? This will be R squared equals to Rn squared. This is the radius corresponding to the various maybe dark and bright rings. This, if you open, this will be R squared minus 2R Tn plus Tn squared. That Tn is the thickness, and when you have this thickness between the two lanes and the plates, that number is very small, and hence the square of that is also going to 0. And we have now this we cancel out, and then you have 0 equals to Rn squared minus 2R Tn. So if you make the subject from this, you have 2R Tn equals to R squared n. And if you divide by R, you have 2Tn equals to R squared of R. Now you see, in the air wedge, we had 2Tn equals to n lambda for the dark. But here, if you're looking for the fringe separations, if you're looking for it means the position, which is given as the radius, the formula says this is the path difference, and for dark is supposed to be n lambda equals to R squared over R. So since in this experiment, it's very difficult to measure the radius, but it's easier to find the diameter. The diameter can be found at the end of you find the diameter, but it's very difficult to find the center, where the center is, because the center is overlapping. So you can talk about the radius. How do you find D? From here we know D equals to Rn. And that's the diameter corresponding to the nth dark or nth bright. It's going to be the second dark, the second bright, and so on. So from here you can find Rn equals to Dn over 2. If you plug here, this in the formula which is given here, we have n lambda equals to d sub n over 2 squared over r. This giving us n squared over 4r. So when talking about the rings, you are looking for the diameter corresponding, because the distance, when talk of the air wedge, we are supposed to find the distance from the center, the second, maybe that was xn. But when talk of the ring, from the center here, we talk of the distance here is giving as the radius. The radius corresponding to the first bright and so on. The center is, that's where the central fringe is dark. It's the dark spot. So the first dark ring is here when n equals to 1. From this, you can find that dn squared equals to 4 n lambda r. This is the for dark. For bright, the formula will be the same, equals to 4. Now what changes here is the n. It's supposed to be n plus a half lambda r. This is 4. This is dark ring. This is bright ring. Here, our n starts from 1. Why? Because at the center, when n equals to 0, you get the first dark, which is given the name it is a dark spot. So we don't call that dark spot as a ring. So the ring is counted when n equals to 1 and so on. But here, the formula starts from 0 and so on. So that's how you can find the diameter corresponding to the different orders of the dark and bright. So you should be comfortable on how to use these two formulas when you are solving some questions. So here, the concept is the first image is dark, which means it forms a dark spot. So the other images will be extending from the center, forming concentric circles. That's why it's giving the name Newton ring experiment. It's a ring. He observed a series of rings around a central point. Now, let's see now example on how to use this concept in solving various questions. Example number 2. The question says, in verifying Newton's ring experiment, a set of Newton's rings were produced between one surface of a biconvex lens and a glass plate using a green light of wavelength 5.46 times 10 to the negative 7, 5 centimeter, I mean. The diameter of a particular dark rings of orders m. So we don't have the order, but this is a dark ring, dark rings. Okay, if it's dark, the first dark is found when n equals to 1. But here, we are not told what is that m stand for. It can be the second order and so on. And now the orders, the diameter of the m order and m plus 10 orders were given as supposed to be 5.72 millimeters and 8.1 millimeters respectively. When observed through a traveling microscope, we saw that. Normally these experiments can be done when you have a strong microscope that you can be able to find the position and be able to find the diameter corresponding to those fringes. This is the part 1. Now, information says that when the space between the lens surface, in between, if you remember, we have a lens there and the glass plate. In between, it's air now. But the space has been filled with the liquid. So if it was being filled with the liquid in between, when you fill here, in between, now the medium will change. We find that the values, instead of being 5.7 or 8.1, they change to be 4.95 and 7.02. Means what? The position, the diameter of the M, it was 5.7, now it will be 4.95. Instead of 8.1, it will be 7.02. That has been now reduced. The question now is requiring what? The question says, determine the radius of curvature of the lens surface. Part A. Part B, what is the refractive index of liquid L? We are not told the nature of the liquid, but the question says it's a liquid whose refractive index is supposed to be found. Then, after finding the refractive index, you can know the name of that liquid. Very interesting question. let's start now. So from this question, you can see it is an experiment which has done. Step number 1, you're supposed to find the radius of curvature of the lens surface. But the formula is talking about the diameter of the dark is given by 4n lambda r. This is the formula you did. So you are told now, let's talk about this. Is the experiment is in air before introducing the medium of that liquid L. So this is the formula for that particular diameter, which is given now m. The order now is supposed to be m, so this will be now m. Now for m plus 10, this equals to 4m plus 10 lambda r. So if you open the brackets, this question number 2, you can find that this equals to 4m n lambda plus 40 lambda r. Let's take this equation number 2 from here. So if you check the 2 equations here, you can see that you can find the radius of curvature by subtracting question number 2 minus question number 1. This will be the diameter corresponding to this dm plus 10 squared minus dm squared. This equals to 4m lambda r plus 40 lambda r minus 4m lambda r. This will cancel out. And you're left with the dm plus 10 squared minus dm squared equals to what? This would be 40 lambda r. You're supposed to find the radius of curvature r, which is given by dm plus 10 minus dm squared divided by 40 lambda. So the wavelength is given. So the diameter of the dm squared, you're supposed to find the diameter corresponding to m and m plus 10. So the diameter corresponding to m order is given as, it was given as 5.72 millimeter. And the order of m plus 10, it was given as 8.1 millimeter. And so the wavelength is given as 5.46 times 10 negative. If you convert it into meter, this will be negative 7 meter. So if you plug the values here, we have r equals to, this is 8.1 times 10 negative 3 squared minus 5.72 times 10 negative 3 squared divided by 40 times lambda. Our lambda is 5.46 times 10 negative 7. Using your calculator, you can find the values. Let's find 8.1, 8.10 e power negative 3, and then square minus 5.72 e power negative 3 square dividing by 40 dividing by 5.46 is e power negative 7. What are you getting? You get something like 1.506 r 1.506. So that is the radius of curvature of the lens. Very easy, and you can see now how do you go about. So everything is given. The order of the dark fringes are not given, but you're not interested to find them. Use the value which are given, the diameter of particular order, and you can get the radius of curvature of that lens. The second part, B, what is the refractive index of liquid used in this experiment? So if you're looking for the refractive index, now this was in air. Let's talk about the arrangement now in what? In liquid. Suppose the liquid is introduced between the two materials. This is now talk of the liquid. Liquid is in between. We know that the refractive index of the material is now given by lambda over lambda of the material. When the wavelength is, this is in air, This is the wavelength in that liquid. So from there you can find now the wavelength which is now given as that. So this is the wavelength which is in the liquid. So here I want to think about this is the lambda. Let's talk about this is the lambda. Use lambda. This is the wavelength in that liquid. It's lambda dash. So we have the first equation here will be dm squared equals to 4m bracket. What is lambda? It's lambda over n. This is dash. That's equation number 1. And then what is our m plus then order this 2 squared equals to 4m plus 10. This will be lambda over n. That is number 2. Simplifying the equations, if you open equation number 1, we have dm squared equals to 4m lambda. There's r missing here, first here. R is missing there. So you have this m lambda r over n. Number 3. Number 4 is d squared of order 10. This will be 4m lambda r over n plus 40 lambda r over n. Number 4. So you're looking for the refractive index here. That is our refractive index. Not the n, is our refractive index. M is the order. So if you take question number 4 minus number 3, if you find the difference, you find that this will be our dm order minus dm plus 10 squared minus dm squared. This give us, if you find question number 4 minus number 3, this will cancel out. We are left with the 40 lambda r over n. If you make n the subject, you find that our n equals to 40 lambda r over dm plus 10 squared minus dm squared. Now these are the values that we know when the liquid was placed between the surface. This is the diameter changing now. The values are given. It's now 70.02 and 5.9, 4.95. We have the values of the refractive index. No, the wavelength is 5.46 times 10 negative 7. We know the radius of curvature now from the experiment that we have. Part A, it was 1.5. And the difference now is you take 7.02 times 10 negative 3 squared minus 4.95 times 10 negative 3 squared. These are the diameters corresponding to the orders m plus 10 and the m when the space between the lens and the glass was filled with liquid. Trying to evaluate the expressions, you can start from the bottom there. Let's take now 7.02 e power negative 3 squared minus 4.95 e power negative 3 squared and inverse multiply by 40 multiply by 5.46 e power negative 7 multiply by 1.5, you get something like n equals to 1.322. So this is approximated now. This is equals to 1.3 because of errors and because of approximations. That is the refractive index of the liquid that was introduced between the surface. That was part B. Part C, what is the name of that liquid? We know the refractive index of water, this is what we have. It's 4/3, exactly 4/3. So this looks like the liquid in between was water. Okay, that's our second example, and we have seen how to use different formulas when solving questions involving Newton's ring experiment. Now let's look now the assignment for you can do. It's different question that we have seen before. In Newton's ring experiment, the light of wavelength 5.46 was illuminated on the top surface of the lens whose radius of curvature is given. Determine the radius of the third ring. Radius of the third bright ring. So the formula for finding the radius, it's better you find the diameter first. So you are told now, I'm giving you the hints. Where do you start? We know for dark ring, the formula equals to 4n lambda r. If you know the diameter, so then you can find the radius, because the radius is 2r. You can take the values divided by 2. So here you can find the diameter. Now, because we are talking about the dark ring, now the first here, we know n starts from 0, 1, and so on. This is giving us the central spot. So the first ring is found when n equals to 1. And the second when n equals to 2. So the third ring is found when n equals to 3. So d3 squared equals to 4/3 lambda r. We take 12 times lambda, which is given as 5.46 times 10 negative 7, you convert into meter, times the radius of curvature 1.5. You can find the diameter for the third. It means you find the square root of that values. I'm giving you the hints, at least now you can check the values. After getting that d, you find r3 as d3/2. So that's how you can find the radius corresponding to that third dark ring. So if you use your calculator, you can find that. Take 12 times 5.46 e power negative 7 multiplied by 1.5, you get 9.828 times 10 negative 6, and you find the square root of that is giving you 3.1 times 10 negative 7 meter. So the radius of the third will be 35 divided by 2. You get 1.567 times 10 negative 3. This was negative 3, I mean. Yeah. So this is the radius corresponding to the third ring, which means it's 1.57 millimeter. So you can find the radius corresponding to the third bright for this part now. For part B, our n starts from 0, 1, so on. So this is the first ring, bright, second, third. So here n equals to 2, and the formula equals to n plus a half 4 lambda r. So I think you can find that. Thank you for watching, and we are sure that after this discussion now, you are comfortable on how to solve different questions concerning about air wedge, Newton's ring, and the Young's double experiment. But stay tuned, more lessons will be coming through here. Thank you and goodbye.